Okay, hi again. The last talk was actually quite nice in that regard. Sorry for the pain that it caused there, what the language can't do at the moment, but that's exactly the reasons that we try to move beyond the expressivity that Solidity has in this regard, even though that means a simplification of the language in the other regard. That's what this talk will be about. So yeah, what I want to start with is what's wrong with Solidity currently, basically. So Solidity has no notion of generics, so you just saw what that means. You need to overload for a variety of types if you want to write a library. That's not even possible in all cases. You need to have external code generation, and it's a huge mess. So that's, yeah. My third point is inferior extensibility. That's exactly the problem that was touched there. What we have instead is an assortment of hard-coded language features that grew over time, which now give us a recipe of what's necessary to have the sufficient expressivity for a smart contract language, but which are not exactly built in the most logical manner at all times. It's a naturally grown agglomeration of different feature requests for people over time. We also don't have a formal semantics in the sense of a real set theoretic mapping in a denotational semantics that you would define a theorem prover or something like that, which would, for a language in our domain, be a really good thing to actually help formal verification and even also below formal verification auditing that doesn't need to figure out what the semantics of the language is, but that is actually formally defined. Problem is, of course, that in the current state of the language, defining a formal semantics is very messy because it has little logical structure, but a high set of special cases that you need to fit together in specific contexts that create different semantics. This also means that introducing new language features for us comes at a very high cost and risk. So, I mean, it's already hard to maintain the current compiler as it is written. It will only become worse if we introduce new constructs of the language as we had done before. Whenever we introduce, for example, transient storage as a new data location that will explode our testing coverage. And yeah, for other features that are requested that we see the need for, the same would hold. So the current approach that we have been following so far is not sustainable long term. On the other hand, we have a lack of features. We can't just stop doing this. We have lack of features in proxy support, in flexible storage layouts, and so on and so on. There's a lot of things that people actively want and need still that the language cannot express. So yeah, I already basically covered that. There is two paths we could follow now. We could keep doing what has been done in the past. We could keep extending the language with compiler hard-coded built-in functionality, which increases the semantics and the compiler further and further. That would mean that we may quickly arrive at some new features that people want, but it will increase the risk of compiler bugs and semantic complexity further and further. The alternative is to basically do the opposite, to reduce language complexity and target a new, leaner, smaller language core, while on the other hand focusing on making actual extensibility an actual thing that's possible with the language. Then that would allow us, as new languages are also talking about, what their goal is, to actually move the feature development of the language to a standard library that then could be developed separately by community, could be audited, verified, and would move complexity away from the actual core language. So yeah, I may have been obvious in what our plan here is. We don't want to follow the first path, and what the second path we want to target with what we call experimental solidity at the moment. So experimental solidity is something we already introduced conceptually. There is a pragma experimental solidity that brings the compiler in a state that has no stability and security guarantees, that you should not use in production, that also tools don't need to bother about. This is not meant as something to use. That's just something that we use to implement and maintain our path to this new language front-end design that we want to transition to, and to especially allow early feedback from the community to what we're doing here. Ultimately, we aim at, in the further future, to transition what this will become to standard Solidity in a breaking release. And we hope that we can achieve a situation in which this will be no more complex than past breaking releases, but hopefully one of the last breaking releases we have to do. So yeah, that's the design goals that we want to target with this approach. I already mentioned that somewhat, but let's be clear about it. We want a really simple core language. Long term, we want a formal, mathematically specified semantics. We want virtually no hard-coded built-in functionality anymore. We want all features and types implemented in a standard library. That sounds impossible, but I think we have an approach that makes this feasible. That's targeted around the type system of the language. There is something called Hindley-Milner style type systems that I'm not sure how many people know as a term. Rust uses type systems based on that. What we target is a much simpler version of that, but the principles are the same. Yeah, it would take too long to explain how these type systems work in detail now, but for experts on the topic, let me continue in how this type system should work. It should be a Hindley-Milner style type system with polymorphic functions. We don't need let polymorphism. That's another detail that makes things simpler. We also don't need type classes in an extended manner. I mean, type classes, if you don't know as a phrase, that's the same thing that Rust refers to as traits. We need that somewhat, but we don't need complicated versions of that. We can get away with a very simple version of type classes. And then the next ingredient that we need is a small set of primitive types that the compiler can understand. For that, yeah, currently call it the word type. That's basically the type of inline assembly. That's the type that you see in UL, which is a 256-bit word, but with no type information otherwise associated with it at all. On top of that, we need the ingredients for defining elder-baked data types, so sums, products, function types. That gives us the ingredients to define all types that we currently have. What we then need is to actually be able to define types based on these new types, based on these ingredients, or more precisely type constructors in language, or in that sense, in language, meaning in the standard library in the first instance. The property of this system, some properties of these systems, if you are a bit of an expert in these topics, will be decidable type inference and principal types. That means that every expression will have a unique most general type. That's a nice expression, and also chaining us to keeping things simple, because if systems get more complex, they lose these properties. But yeah, I also won't get into that much further. And yeah, we need inline assembly. Inline assembly will be our backbone with which we actually implement features then. So yeah, features and types in standard library will have base cases implemented in inline assembly. Those base cases can be composed together to more complex structures. Types can be categorized using type classes. Type classes allow inductive constructions on types, like for ABI encoding. We can implement ABI encoding in language as type class instantiations over all types, which should cover all features we currently have, and will mean that all complex language features become even self-specifying in a sense, since you can look up its definition and how it's constructed in language in a standard library. So yeah, there's still different views on what will happen here. These changes are more targeted towards us and to library authors than to end users, really. What an end user in the end will see is some more expressivity, like in the last talk people would actually need and want, but also more like we will have some syntax changes. It will be a breaking update, but with a reasonable upgrade path. There will be some new restrictions to keep the system simpler, where the current type system is actually more specific than for its own good. For example, implicit conversions will probably fall out. But yeah, we will get faster and safer language extensions that indeed don't need to touch the core language, but will arise from standard library development. On the other hand, for us implementing the compiler, And for library authors, the picture is more interesting, really. Since the feature implementations will become mostly written in Solidity itself, that's a change for implementing features. Implementations of those features can be shared between implementations of compilers. We get for library authors advanced features to construct new types. Those features can become safer because they become auditable and verifiable without digging into a C++ written compiler. And yeah, the next one I already mentioned, but yeah, the standard library also ideally would then become a community effort, really, that has a formal proposal mechanism that involves, we'll get later to that, but that involves a proposal, iterations, auditing, verification, and standardization. That renders a bit weirdly. Not sure that's the worst problem people may have with that. I hope the other slides will work better. Anyways, we will have some syntax surprises that we currently target to have with these changes. One of the most visual ones will be that we want to use postfix types. That's something that has been requested since basically forever, which has significant advantages if you want to get to a place where types are no longer a specific set of built-in types, but you can get complex type expressions like function types and tuples or sum types, which we need as basic building blocks. Currently in the language, we don't have a huge parsing problem, or only a minor parsing problem, because the set of types is rather small, whereas, postfix types generally make parsing easier. It's something to get used to, but I think some people will actually be happy about us moving that direction. Then, to actually get to generic functions, I'm sorry about the layout of these code fragments. I'm not sure they seem to have messed up indentation in some copying process. But yeah, we will have type variables. I must say, we currently don't, we should emphasize that and have emphasized that before moving to the code slides. We are not working on final syntax right now. This is placeholder syntax. We will gather community feedback about syntax we use for these things. But conceptually, what we want to have is functions that accept a variety of types organized into type classes. Here we have a function of doubling all things multipliable, which ranges has a type that they depend on, which ranges over all types, satisfying the class of types that are multipliable. We get type inference, which you maybe used from Rust. So we don't need to actually be specific about this variable having the mentioned type, since that can be deduced from the right-hand side. That's something that, also we expect people to be wary about in the beginning, but if you ever have worked with a system that has these kinds of properties, you will grow to like the ability of being able to not specify types everywhere. If you don't like that, we don't prevent you from specifying types everywhere. This can actually be taken even further. We can actually even let the signature types be deduced, because we have the property of decidable type inference and principal types. So every expression has a unique most general type, which can be inferred by the compiler. I don't think we will see that. We may actually even prevent that from happening at the compiler level itself, but it's an interesting fact that this would be possible to actually even allow not specifying signatures in types or types in signatures and relying full on type inference. These code slides are really bad. Again, sorry about that, but this is a possible definition of the class of multipliable types, which just defines an interface over types that has a single function multiplying that same type with that same type, resulting in that same type. What keeps the system simple is restricting this to a single type variable. That makes these type classes basically properties of types and not arbitrary relations on types, which needs a full solving engine to actually then resolve that Rust has. If we keep it to properties of types, the solution process for these things remains extremely simple, and it's just basically set operations. It's set unions and set intersections and set containment that actually give you enough material to resolve type classes. Type definitions you should already be used to from the user-defined value types. Then we can introduce new types based, we have here a definition of UN 256 based on the primitive word type, which is how UN 256 works. It is represented as one EVM word. And then an instantiation of the class of being multipliable for this type that implements the multiplication function. You can access the underlying type of our type definition to get the word representation. We want to restrict inline assembly to only accept variable references to variables of that word type. That will prevent us from almost the vast majority of bugs that we had in the past that involved inline assembly that were due to cleanup and conversion behavior from types from and to inline, during inline assembly transitions. And yeah, then can encapsulate the type back to the defined type. Yeah. Type inference could, again, allow dropping a lot of these types because they can be inferred. Just to say, this syntax is temporary. We are not currently concerned with syntax, but only with logical structure. We could also just go a more Rust approach here, consider this type class a trait, then not call it instantiation of a type class, but implementation of a trait for a type. As I said, this is still also early stages of implementation for the basic logical system. We're not concerned with syntax at the moment. So yeah, the question is, how far can this approach be taken? An example of multiplications is rather simple, but the ingredients I've shown you should be enough to basically make all high-level language features definable. That includes data locations. So the data location of a type being in memory can just be represented as what actually happens is that on the language level you have a pointer to memory. So we can define for any type A that type A living in memory is a pointer to memory. Whereas then loading from, writing to, all the data locations can again be implemented using a type class instantiation system. So all of these hard-coded constructs will vanish from the compiler and move to a standard library. ABI encoding, again, also becomes a type class that will range over all types, so we will have inductive constructions over all types, but it's possible with these simple ingredients. Dispatch generation is just a higher order function in the sense that it takes functions and creates a dispatch out of the functions and their selectors. So all the complexity that's currently hard-coded in the compiler will vanish. The source of truth of what the compiler does then moves from magic hidden in some C++ implementation to the inline implementations you can actually look at. What the compiler will keep doing as what's used to be code generation is monomorphization and type unfolding. That basically means moving back from generic functions like this one to all the instances of calling this function, which will always have concrete types, to inserting the concrete type into the implementation and tracing from there. And we go back. Type unfolding means moving from defined types to the underlying types. The result of that process will basically already be YUL. You will have functions with only word types or tuples of word types as signatures, returning only those. That's basically YUL functions. So code generation basically vanishes. And yeah, in general, stuff that people, I think, would generally want that is enabled by this in principle is that you can actually have generic abstractions and encapsulations of inline assembly. Use inline assembly for the low-level implementation, abstract that into nice type constructs. So in this version, you can think of, in this concept, you can think of assembly blocks as what Rust has as unsafe blocks. So inline assembly will give you low-level access that you need to be sure about, or you need to know what you're doing, as always. But it can be encapsulated and abstracted over in a generic manner now. Now, that may all sound great, but to actually get to a place where this is nice and usable, we will need syntax sugar on top of this logical structure. For example, a simple contract definition can be thought of then as sugar over a dispatch generation and storage layer generation, which both can again be defined in language. Here we have some options. We're currently not considering syntax, let alone syntax sugar, but in the future we will have several options to take that. We could either construct syntax sugar that get us very close to the current version of Solidity to make the transition easier, or this could be an opportunity to improve the syntax and change some paradigms away from how the language is currently working. We will work on that depending on our conversation with the community about that when we are at that point. Which gets us to the sad part about this, because this stuff will take time. I can only guess about how much time that will take, but yeah. We have started on a branch so far that's not merged and not actually usable under the experimental Solidity pragma, but will be at some point merged, a prototype of the very basics of this new kind of type system that is very restrictive still, only as value types and single parameter type classes without associated types, which we may need as one last concession. Still working on trying to avoid that. It will be a limited version of associated types if we need it. Ideally, we wouldn't need it. Anyways, later in the course of 2024, we hope to extend this prototype to reference types, to all the expressivity of type classes that we will need. By the end of the year, we can build start a standard library development process. But we won't target syntax sugar at all next year. So even if we start developing a standard library, this will be on hard-to-read low-level representations of these constructs, and syntax sugar will be a process that only comes later. So to guess further and further, no idea if this will work out like that. But in 2025, I could imagine that we have an actual process for improving the standard library. We stabilize the type system, and we actually introduce the syntax sugar, and maybe then, even further in the future, this actually becomes stable. So this is the proposed path to maybe arrive at a version of Solidity that could actually become Solidity 1.0. Before that, I don't think we can accommodate that, and we don't have sufficient expressivity, but this will hopefully bring us there. To elaborate a bit further about how we imagine Solidity feature development to work in this new world of this new type system is that there is a feature request from the community, that we will have a standard library improvement proposal arising from that feature request, which leads to an implementation of the feature in language, not necessarily done by us as the compiler team, potentially a definition of required syntax sugar, and a feedback process leading to a final draft of a proposal to amend the standard library. Then we hope that we can actually engage auditors and formal verification experts into that process to actually verify this proposal, and hopefully make it good tone for any auditing company to actually have verified most, if not all, of our standard library. And once the proposal is thereby validated and trusted, it would be shipped as the compiler standard library. The entire process hardly involves compiler changes. The only thing that is a compiler change in here is potentially the definition of required syntax sugar, which we could still even outsource out of the compiler into a description language. Rust even allows in-language syntax sugar definitions. I'm not sure that's a good idea for us ever in the future, but also potentially an option if there's demand for that, but we're talking further future here anyways. What this means is that core language changes would actually become very rare. If they are at all necessary, they would originate from standard library improvement proposals, just in case that somebody wants to improve the standard library in a way that requires more expressivity in the core language, which would have a high bar of, needs high justification to become considered, I would imagine. Which means the core language stabilizes, but we can still meet the community demand for new features as a collective effort of the community in standard library development and auditing and verification of that standard library. The entire construct also allows for further flexibility in the future. We could possibly maybe not ship with the compiler, but have external variants of the standard library. So the standard library itself can contain types that have checked arithmetic or unchecked arithmetic. That's also a variant already, but could be that I expect to be shipped in the compiler standard library because people want and need that. But we could also have, besides the stable and validated standard library in the compiler, some community contributed library that is much more aggressive in optimizing and much less concerned with safety features, which is also something I think the community may appreciate. And yeah, we could have standard library variants for L2s or for whatever purposes that require having different constructs on top of you, basically. So yeah, that's our long-term goal with the language. Wondering what the reactions for that will be. I imagine there's questions, so I would be happy to take them.
Yes, do we have any questions? Yes.
Thank you for the presentation. While you are working on all that great stuff, what will happen to the 0.8 line of Solidity version? Do you expect to ship some features at all, or just only bug fixes in the near future?
We try to keep development of the current stable version of Solidity at a minimum. So if there is high community demand for something that we can do without stalling this even further, then it will take a long time. We will consider that. But the larger items that we had planned will be so much simpler and more safe to implement in this new paradigm that, yeah, we don't intend to do that in the current version of Solidity. But of course, bug fix and maintenance will happen, of course.
Hello? Cool. Very exciting. My question is, it seems like there's not much in the backend that's shared with the current version. Is that correct?
That's actually the nice thing. This is actually, in that regard, not as an aggressive change as it may seem. What we have as via our code generation is basically the same thing already. It's just not a typed in-language definition of the features. It's just a string templating engine we use in the compiler internally. But that would basically just need to port from this internal compiler via our pipeline to language.
Cool, yeah. My question would have been, what's the decision process behind basically making this Solidity versus just making a new language that implements all of this? But yeah, that kind of explains it. Cool.
Anybody else? Any other questions? Yes.
Hello. Since this paradigm, this new kind of improved syntax of Solidity is being designed, don't you think that when it comes out, Solidity will have the same structure that Scala had when Scala 3 came out? And now we have two communities that are either supporting Scala 2.4 or Scala 3.
I hope that what we're building here will be universally superior, so that problem won't happen. How the precise syntax will work, as I said, is still open for discussion, and we have the option to keep it extremely close to what Solidity currently looks like. So that would also be a mitigation strategy if this is something that starts to be visible on the horizon.
Okay.
Thank you for the talk, really exciting updates. I have a question. You mentioned earlier that this is experimental mode is not for production use, but is there going to be any, do you imagine like there's going to be any hard enforcement on that? Because if people can still use experimental features and deploy it to the blockchain, it means that others and other tools are now basically need to support it as well. How do you think this can go?
In the process of developing this stuff, the first versions will not possibly lead to something that will lead to something that can actually be used to deploy things on chain reasonably by anybody. So I don't see that as a danger. So I mean, there's two reasons why we actually introduced this pragma and want to ship that as a development process alongside in the compiler. That's maintenance ease, to kind of like not having to maintain a branch concurrent with the maintenance we do on the rest of Solidity, and early feedback. I mean, we have tried to get feedback on features we developed in the past that live only on branch that never worked out. So since this process is in requirement of feedback on the syntax side, that's why we choose to use a pragma approach and expose it early, even though I don't think there is risk of seeing this in production until a much later stage.
Hi. Yeah, thanks for the talk. Is there also a push to have more safety features that are, for example, enabled in Rust, where you have result types that have to be explicitly handled? At the moment, we see many compiler quirks, like weird edge cases that security engineers need to be aware of, and they know about this. But like things that the normal user wouldn't necessarily know about. And if we had these kind of like, or if we were more focused on security with the syntax, then you might force the developer to explicitly handle these cases instead of making the compiler insert some like random unknown revert cases, examples being like ABI decode, having reverting cases, yeah, or just like overflow, for example.
Yeah, I mean, the idea in this transition is to hopefully remove most of the corner cases in that the type system will be constructed logically and more uniformly. So that's already a gain. End users I don't see using these features. I don't think that auditors will and should accept code using extreme inline assembly in generic functions. So I imagine that to be reserved for the compiler implementation of the standard library and for proposals of improvements of that, or for separately audited export libraries. That's also mitigating that. As for safety features in the type system itself, that's worth a thought. We want to keep the system as simple as possible, and implementation of the system and being able to follow the system as simple as possible. We can consider introducing a notion of linear types as a future step towards that, but in the first implementation, I would say it's more important to keep this as simple as possible.
Yeah, I mean, I'm very excited, obviously. Question, do you have, or do you plan to have some kind of support for function decorators for pre-post conditions, and also, for example, I mean, you could easily implement Viper's locking using a decorator, right?
I mean, in the further future, I would say, I mean, I don't want to implement or integrate undecidable solving processes into compilation or something like that. So that's something that we would like to avoid. On the other hand, there is subsets of refinement types and decidable fragments of logic. That's something that we could, in the further future, also consider introducing as a language extension, but I would say that's also speculation of far future. So would like to see that myself, but it's also currently not not on the agenda and far future speculation.
Thank you for the talk. Just a quick question. Will we see the transient storage supported in the upcoming versions or only after those big changes are implemented?
I think the community would strangle us if we didn't implement transient storage in some capacity before this will be ready. The worst that can happen is that we only expose it in inline assembly. Then it depends on community pull.
Okay, so no high-level Solidity support for transient storage, only with inline assembly.
We'll start with an inline assembly implementation, so exposing the opcodes for tstore and tload in the U level, then a value type implementation, still in scope. The feature parity with storage otherwise, we'll see demand.
Yeah, thank you.
Did I get this wrong, or didn't Haria already implement access to tstore tload in inline assembly? Or it just needs to be merged?
Second?
Isn't access to tstore tload in inline assembly like already have a implementation?
I mean, it's trivial to do. It's not merged in the current
Right,
compiler,
right.
but I mean, it's trivial to do.
That's what I thought.
We will do
Okay.
that soon.
Great.
Anybody else?
Thank you so much.